Start. So welcome back to our last week of class. Hopefully have enjoyed the musical interlude. So we have our very last quiz to go over today, different in nature than the others. We're going for more big picture here. So each of you should have completed this, hopefully, or at least worked on it. So let's do it. What role do time invariant predictors play in the model for the means? What do you think? What do they do? Big picture. What are they for? What do they do? In the examples we saw last week, what were the types of effects that we talked about? Want to try? Moderate what? Time. And also what else? What do they do as a main effect? As a main effect, they moderate time? No. What do they do as a main effect? Intercept, yes. They moderate the intercepts and the level 1 terms. So if you have, say, a quadratic model of change, you can have a time invariant predictor that moderates the intercept. It can moderate the linear slope, and it can moderate the quadratic slope. If you have, say, a piecewise model, we looked at an example that had 2 linear slopes, it can moderate each of those as well as the intercept. So that's, in general, what it's for. How does one assess significance and the effect size of a specific effect? For instance, the effect on the intercept specifically. So how do we know if that is significant, different than 0? Don't think too hard. Can we stare at a p-value? Yeah, we did it all last week, right? So yes, we can have the estimate divided by its standard error. Treat that as either a z or a t, depending on if you want to have some denominator degrees of freedom. I call that a wall test, a univariate wall test. If we want to test a group of effects, is that another question? Let me see, I don't want to give it a... Yeah, yes, that's the next question. I won't go there yet. Specific effect size then. What if I wanted to talk about an effect size measure specifically, say, for the effect of a time invariant predictor on the intercept? What could I do? I'll give you a hint. Some kind of R-square. Pseudo R-square for the intercept specifically. Likewise, if I wanted to talk about the effect of a time invariant predictor on the time slope, then I would need a pseudo R-square for that random time slope variance. So it's whichever variance component goes with the moderation effect in question. If I want to talk about question 3 here, significance and effect size for the overall contribution of a predictor. So grouping all of its effects together. So for instance, last week we had the effect of baseline age on the intercept and on each of the time slopes. If I wanted to lump that together to say what is the total contribution of those 3 fixed effects of age, how do I talk about significance for that? What can I do? Total R-square would be effect size. So yeah, we'll answer that one first. Yes. So how much total variance, everything put back together again, do those 3 fixed effects account for? How about a significance test to go with that? There's 2 options you should know. If you're using maximum likelihood, regular flavor, what can you do? Think nested model comparison, right? You can do a likelihood ratio test against a model without those predictor effects if you're in maximum likelihood. But what if you're in residual maximum likelihood, REML? Then what can you do? Because you can't do that. Give you a hint. In the software, it's specified using an option called contrast. So it's called contrast in SAS and Stata. It's called test in SPSS, and it's called model test in M+. What does that do? Yeah, multivariate wall test. And again, if you don't have denominator degrees of freedom, it comes out as a chi-square. If you do, it's an F. But same idea, you're testing multiple things at once, whether that set of things is different than 0. And then that's it. Last question, theme song. So I'll go over those later. So any questions on the quiz? Do you guys see the answers when you log in? Are they there? Or is it just what you wrote? It's just your answers? Okay. Yeah, I imported these quizzes from our old course management system, and I thought it was going to show you the answers, but I will manage to get that, try and get that working, because I know I have answers buried in here somewhere. I just have to figure out how to make it so you can see them. So, okay. All right. Then if no one has questions on that, homework 7 looks like it went reasonably well. If there's any of that that you didn't know why you missed something, please let me know and I'd be happy to chat with you about it. I apologize for the copy and paste error for the deadline. Who is it that emailed me? Was that you? Yeah, she's like, I'm pretty sure it wasn't due December 2017. That was the last time I gave it. It was due. I forgot to change that. So I fixed all the fake late points and everything should be fine. Homework 8 is due at the end of finals and you have enough. You know everything you need to know to do it. So I won't have office hours next week, but I will be on email, and you can ask me about that either today if you started or on Thursday. So, any homework 8 questions? I didn't assume so, but I thought I'd ask. Yeah. No. Not yet? That's cool. That's fine. It's, I'm doing my due diligence. All right. Then we have some new stuff. So while you were gone, we took a vote and decided to do something different this week. Right. So we're doing multivariate models, talking about basically what you do with level 1 time-varying predictors. And the right answer is a multivariate model. To explain what the problem is with other ways of doing it, I threw in a few slides from another lecture that I would normally give before this one. So now we're into what I typically do in my advanced class. In the past, when I've taught this class, there's always been another one that followed right after, where we continued building on the models, getting to time-varying predictors, multivariate, and other sorts of things. So I'm going to try and shove that all into 1 week, because that's what we've got left. So we talked about time-invariant level 2 predictors. So we're picking up, yeah, and I forgot to change the bottom here of this. This is where, if you want to get this lecture in full, along with more examples, you can go to that class, the CLP 945. But I'll fix that here. Gesundheit. So let's do that. We have a lecture 9 then. So time-varying predictors, level 1 predictors, things that are measured at the same or nearly the same occasions as the outcome. That's what we're talking about. Regardless of what kind of model you have with respect to time. So whether you have within-person change and you've modeled that with fixed and random effects of time, or whether you don't have any systematic change because it's just fluctuation, either way, what we're talking about is the picture on the right here. It's the idea that whatever systematic effects of time you have in the data are already in the model. So we're talking about the residuals of what's left. So think about what's left in the level 1 variance that is not about what time it is. It's whatever else was going on at that occasion, because if you have any systematic trends at the average level or at the individual level, they should already be in the model at this point. The reason that this is so complicated, and the reason that this takes like a good 8 weeks normally for me to get through all of this, is because time-varying predictors are almost always an aggregated effect. To the extent that we have within-person variation, level 1 variation, that has an effect in the model. To the extent that we have between-person variation, that has an effect in the model. And a proper model has to have a different relationship between the predictor and the outcome for each distinct kind of variance. And so this part of the lecture here, we start off with just the simpler case in which X and Y just fluctuate over time, but they don't have any time trends. So think about like stress predicting mood, where people aren't getting systematically happier or sadder. They're not getting systematically more stressed out as time goes on. These things just fluctuate together, and that's how you want to know if they're related. So time-varying predictors almost always have at least two different kinds of effects. So if I think about stress measured every day, it's true that some occasions are worse than others. So within yourself, some days are better than others. That's within person variation or fluctuation. It's also true that if you tally up persons' responses in total, some people are going to have higher average levels of stress. They're more stressed every day relative to someone else. That's actually between person. So even though you're thinking of stress as a level 1 time varying predictor, it also has level 2 between person variance to the extent that its mean differs across people. So for the same reason that we have to have between and within person variance in a time varying outcome, we have to worry about between person variance and its unique effect in a time varying predictor. And there's an easy way for you to determine whether or not this applies to a given predictor, because a predictor has to have variance of a particular kind as a logical prerequisite for showing an effect of that kind. So for instance, the level 1 predictors that we've seen so far have just been our time variables, right? Linear time, quadratic time, slope 1, 2, slope 2, 6, all that stuff. Time is a time varying predictor. But in the examples that we've seen, time has been balanced across people such that everybody had the same set of observations 1 through 6. In other words, if we put time, the variable itself, as an outcome in a model, and we ran an empty means random intercept model to get its intraclass correlation, what would it be? If we have a time variable where everybody has the same set of occasions, and we tried to estimate an intraclass correlation for it in an empty model, what would it be? Everybody has the same. So what intraclass correlation would we get? Zero, exactly. It's all within. Everybody's on the same time schedule. Therefore, in the examples we've seen, time is purely level 1 within persons. So we were able to put it directly into the model and know that whatever effects that it had to be within person level 1 effects. It only had that kind of variability to begin with. Therefore, the only thing it could possibly do is give us within person effects. Now think about something where we have both between and within person variation, like stress measured over time. If it has an intraclass correlation greater than 0, you know there's at least some between person mean differences. Those between person mean differences can have an effect. If it has an intraclass correlation less than 1, we know it has at least some within person variation. That within person variation can have its own effect. So anytime you have an intraclass correlation for a time varying predictor between 0 and 1, you have the presence of each kind of information at a minimum, and therefore you need to have 2 effects in the model at a minimum. Only when it's 0, you don't have any between, or 1, you don't have any within, would it only have 1 effect. So here is an example of hypotheses and results that may or may not be in the same direction across levels of analysis. So stress predicting health, for example. We might have a hypothesis that stress is bad for your health. That seems like a reasonable hypothesis, right? Any health psychologists here today? Would you like to become one?
No, it's not.
No, you know? Okay, I'm going to be a health psychologist today. I actually have a publication in health psychology, as it turns out. Would. My hypothesis is that stress is bad for you. Now, how do I express that if stress and health are measured longitudinally? There's at least two possibilities. Number one, people who are more stressed out chronically than other people have worse health than other people. I don't need a longitudinal study to see if that's true. I only need a cross-sectional study. Because the only inference I can make if I've measured each person once is that it's a between-person difference. People with more stress have worse health than people with less stress. The same could be true in a longitudinal study if I took an average of all the stress measurements for a person and I related them to an average of all the health measurements for a person. Within persons, it may also be the case in a complementary way that when you are more stressed than you usually are, you feel worse than you usually do. Same idea, different level of analysis. Both of those things could be true or false or one or neither or both, right? They're logically separate answers to the same type of question. So when you're phrasing hypotheses in longitudinal data, you have to be more specific than just these two variables are related. At what level are they related? It's also the case that you might have effects in opposite directions. So this is an example that is in the book. So exercise and blood pressure. To the extent that low blood pressure is a proxy for good health, people who exercise more and who have lower resting blood pressure people who exercise more have lower resting blood pressure. However, when you are actually moving, your blood pressure is higher than when you're at rest. So one relationship is positive and one relationship is negative. And yet they're both true. What blood pressure means differs across levels of analysis. It can be a proxy for general fitness, or it can be a moment-to-moment indicator of activity level. It's both. So for reasons that are more theoretical or conceptual, these variables may mean something at different levels of analysis, but also just more to the point in terms of numbers. These variables are on different scales. Only if you have two variables, even if you standardize an x and a y to the same scale, they would have to have each the same intraclass correlation for their relative variances to be the same. Otherwise, these two different types of effects between and within will differ numerically simply because they are unstandardized effects on different scales. Because each is relative to its level-specific variance in x and y, and only when they're truly equal do they have the chance of being literally the same number. Okay, with me? All right, so there's three kinds of effects that people talk about trying to obtain when you have these time-varying predictors. The first two is what we've talked about, but to be more concrete, so if I just use x as a generic term for any predictor, it's the idea is, do people with greater values of x than other people have different values of y than other people? And if that is true, that between-person relationship should explain random intercept variance. Also, at the same time, if you are higher on x than usual, is your y higher than usual? If that is true, that within-person relationship should explain level 1 residual variance. So each level has its own predictor, its own effect size, its own conclusion. The third one is grayed out for the time being because I don't want to have to talk about it yet, but it's coming. So here's what people do typically in such situations. And when you only have data where time is not relevant, it's fluctuation data, this could be a reasonable approximation. So almost universally, what they will do is take the level 1 predictor and compute the person's mean of it across occasions. You would then center that person mean at a constant so that 0 means something, and that new person mean predictor goes into your level 2 model. What happens at level 1 is where the confusion arises. There are two main ways of putting in a level 1 predictor. And these are known sort of generally as either group mean centering or grand mean centering because these came out of the clustered data literature. In our context, we're going to refer to the first one as person mean centering. But more broadly, these two centering methods differ in whether you are centering at a variable or a constant. And so in the book, I start using the terms variable centering or constant centering because that's really what we're talking about. In the first one, we center the level 1 variable using the person's mean. In the second one, we just pick whatever constant so that 0 means something. And these two choices will change what your model means. And it can be the case that you have the same model, but the parameters are rearranged, or it can be the case that you have screwed it up. The number one mistake people make in multi-level modeling by far is screwing this up, a problem that I refer to in the book as smushing. That's my term. I put it in the appendix and everything, the index. So here's what not to do. Okay? Wrong way. Bold print, capital letters. This is smushing, this is bad. So let's say that we have a level 1 model where this is fluctuation data, so we don't need time, and I put in a variable time varying x here. And let's say that I've centered it the original time varying x, xti minus c, where c is just a number. So if this variable already had a meaningful 0, you wouldn't even need a c. But if it doesn't, you subtract a constant. So I just go ahead and stick that time varying x in my level 1 model, and I have a fixed effect for it. What's the problem? Well, if time varying x has level 1 variance in it only, this is fine. But if time varying x has level 2 variance in it also, if some people say are more stressed than others on average, if there are mean differences between people in this time varying x, this is wrong. What you end up with is the fixed effect is what's known as, to me, a smushed effect. Synonyms for this that sound more formal are a convergence effect, a conflated effect, or a composite effect. Generally speaking, what the problem is that this TVX is two different things. It's both why are some people higher than average, each other, and why are you sometimes higher than you otherwise are within persons. It's two things, but you only gave it one fixed effect. So that one fixed effect has to do both at the same time. It assumes the between-person relationship among the means is the same as the within-person relationship among the deviations. This is what's known as smushing. Graphically, I'm trying to depict it like this. So we have our outcome y that we originally had all the variance in, and we let the model partition its variance into level 2 between person intercept variance, and then we let the model partition it out of that level 1 within person residual, right? So this is our level 2, this is our level 1. X over here, we haven't partitioned. It's just the original variable. And we put that one effect in the model. That means that one effect has to do both. And it's assumed that it's predicting each the same way. This is almost always going to be wrong. Very, very rarely have I seen it not be wrong. And that's usually in clustered data where the ICC is tiny, so there's barely any between to worry about.
So you mentioned like 2 slides before that the level 2, but the between person and the within person effect can be like in the same direction or in the opposite direction.
Sure.
So when you smush them together, so those effects can be interpreted like in the wrong direction.
Oh, it's meaningless. Like think of this situation where one is positive and one is negative. Like the smush of those is going to be weighted by the relative amount of information at each, So it'll be closer to the within than between. But yeah, you can envision a coefficient near 0 because you've smushed a positive and a negative together. That's bad, right? We can all agree that's bad. So when people say, I grand mean centered my level 1 effect of X, you have to make sure that this isn't what they're talking about. This is bad. Later on, I will show you a way, I don't know if I included those slides, how to fix this. But the way that I fix it in longitudinal data is to avoid this problem by creating the 2 variables for each level myself. So here's what we can do instead. This is person mean centering or variable-based centering. Rather than putting in the original time varying X centered at a constant, I'm going to make 2 new variables. At level 2 is the person's mean. So my variable PMX is the person's mean centered at a constant so that a 0 value is meaningful. Pick your favorite constant, whatever. So if I pick the sample grand mean of the person means, then I would interpret relatively high values on PMX as people who are higher than other people. Relatively low values would be people who are lower than other people. But than other people is the critical thing. It's like a 1 unit difference relative to what becomes really important to keep track of because it's the same variable in 2 different ways. So this is more than other people at level 2. At level 1 then, we take the original time varying predictor and we subtract the uncentered person's mean. In other words, we are taking all of the between person mean variance out of the variable. And what's left within person X is 0 when you are at your own mean, whatever that happens to be. A positive value of within person X means I am higher than usual. A low value means I am lower than usual. What usual is up here in level 2. So these 2 new predictors are orthogonal. They are uncorrelated. They each go into the model at their own level, and their interpretation cannot be screwed up. That's the beauty of this system. So then the model would look like this. So at level 1, we put in this within person X. The only kind of variation that it has is level 1 within person variation. Therefore, its fixed effect in the model, this gamma 1O, can only be the within person effect of having more X than usual at that occasion. Likewise, person mean X only has level 2 between person variation. It gets a fixed effect in the model that's separate, gamma O1. Because this predictor only has between person variation in it, gamma O1 can only be the between person effect. Easy peasy, as my son would say. So each has its own job to do. Within person X goes into the model to explain E. Person mean X goes into the model to explain U0. Cool. So when I do longitudinal modeling with time varying predictors, I do it this way. Because if you leave out either of these, you're just assuming that the missing thing is 0, the same as usual. So if I don't have person mean X here, this is still just the level 1 effect of X. Within person stays within persons because you made the variable that way a priori. Likewise, if I put in person mean X by itself, I know that's only between. Doesn't matter if the analog within is within. So you can't screw this up. That's why I recommend it. So in diagram form, it looks like this. Rather than putting the original X into the model, we have created 2 new observed predictors. That's why I'm using boxes here. Level 2, between person mean variance, and level 1 within person deviation variance. And then each has its own job to do. Between person effect, within person effect. So this is nice, right? Because it's symmetrical. Right? Makes sense? But then you're like, wait a minute. Why does X get boxes and Y get circles? Isn't that kind of arbitrary? In other words, we let the model, we let the model split up the variance in Y into estimated variance components, right? And we talk about random intercept. Random intercept is between person mean differences, right? And we let the model figure out within person level 1 variation around those means. Well, we're doing the same thing by brute force by making these observed predictors. Person mean is the analog to random intercept when the model finds random intercept for us. This within person X, where we've deviated each observation from the person's mean, is the analog to residual variance. So if that's the case, why don't we just treat X like we treat Y and turn them into circles? That's what we're going to do. That's where we're headed. But before we stop there, I have to introduce one more concept, because that concept, unfortunately, is going to come back to bite us in the ass when we interpret these models in M+. Technical term, bite us in the ass. Are you familiar with that expression? No? Well, it's kind of what it sounds like. It is going to cause difficulties, such as an angry dog who bites you in the ass. So the two things that this version of the model here can tell us: between person effect, within person effect. Cool. What's the third thing that we might want to know? What this specification does not tell us directly is something called a contextual effect. A contextual effect is another type of level 2 between person effect, but it means something different. There are two ways to look at this idea of a contextual effect. The easier one is simply to ask whether this fixed effect from the person mean to the random intercept is different than this fixed effect of the within person to the residual. Are these two fixed effects the same or different? The difference between them is called a contextual effect. In longitudinal data, that is almost never of interest. It is of interest in clustered data much more frequently. The difference in terms of what contextual means, because it's another type of level 2, is after controlling for the level 1 predictor's value at a given occasion, what is the incremental or unique effect of the person's mean specifically. That's the conceptual interpretation that goes with this. So the other way that people specify these models, which is much more common in, clustered data, is to not do the person mean centering, to leave in the original level 1 predictor centered at a constant, to go back to grand mean centering. Now that was the thing that I told you was wrong. Here's how to make it right. So this specification, I've changed the colors to indicate that the variables and their interpretation have changed. So time varying X is in level 1. That's the full version of time varying X just centered at a constant. So this level 1 time varying X predictor still contains two different kinds of variation. It contains level 1 within and level 2 between. All of it lumped together still. However, now it is competing against person mean X, which is also in the model. And that's why this is okay as an alternative. There's nothing wrong with this. But it's important to recognize the difference in what these parameters now mean. So person mean X is only level 2. Level 2 between. So if you think back to regression, if you put one predictor in the model and you add in a second predictor. Each of their effects when they're paired together will be different than their effects when they're by themselves, to the extent that the predictors are correlated. It's the idea of a unique effect after controlling for the other predictors, right? You're familiar with that. So if we think about what is unique about each of these predictors, that's how we figure out what the hell they mean. Okay, so time-varying X has both between and within. Person mean X has only between. So what is unique about time-varying X? The within. So now, magically, its level 1 effect here, this gamma 1O, becomes the within effect. It occurs through statistical parceling. It occurs because it has been appropriately controlled for the level 2 part. So it has to become the unique effect, which is within. And that's why it doesn't really matter in terms of whether the model is wrong, whether you use person mean centering or grand mean centering for level 1. So long as you have the level 2 part in also, the level 1 predictor becomes the within effect just like it should be. The key is that you have one predictor per level that the predictor has variance. That's the key. Now, what person mean X's effect becomes is the contextual effect. And it's going back to the idea of a unique effect. Time-varying X has level 2 between in it. Person mean X has level 2 between in it. So these two things are competing against each other. Therefore, the effect of person mean X, gamma O1, has to become the extra effect of the person that's not already implied by the time-varying X being in the model. It's really confusing in longitudinal data. So time-varying X is being controlled for not just its relative value, but its absolute value here. So this is the effect of being, say, a grumpy person after controlling for exactly how grumpy you are today. It's like, do the rest of your predictor values sort of make a difference that isn't anticipated based on just today? So I can give you a different example that makes way more sense in the context of clustered data. Let's say that we have something like student achievement predicted by, we have something like student SES measured however. Okay, so is being relatively well off good for you? Now I'm an educational psychologist. I think that richer kids get better grades. How about you? Sure. Now, how does that happen? Do richer kids go to better schools and that's why they get better grades? Or is there something just inherently better about being from a rich family? Well, I don't know. Are students randomly assigned to schools in this country? In any of the countries where you used to live? Nope, right? Here it's based on property values, like you go to the school that's in your neighborhood. So if you live in a really nice neighborhood, you go to a really nice school. Yay for you! So a way that we might approximate that is to also include school mean SES as a way of talking about the context in which you go to school. So if you want to know what the incremental effect of going to a good school is after controlling for how rich a given kid is, this is your model. You would put in student SES, subtract whatever constant to make it meaningful. You would put in school mean SES, subtract whatever constant to make it meaningful. You would end up with the level 1 effect of student, which is the effect of being having more or less money than the kids around you, and then the contextual effect of what is the extra effect of going to a rich school after controlling for how rich you are. Contextual. I mean, it literally is that's why the term came from. It's the extra influence of the context. So this model is way more useful in clustered data, whereas the person mean-centered model, where you have this clear between and within, is way more useful in longitudinal data. The difference is that in clustered data, each level has a unique entity. So if you think students in schools, kids are kids, schools are schools, right? But in longitudinal data, what's level 1? It's time. Time is not a thing, right? Like it's not a unique thing the way a student is a unique thing. An occasion is really not a definable unit. It's only relative to something else. So this idea of controlling for the occasion just doesn't map the same way that it does in clustered data. So point being, to be correct, time-varying predictors go into level 1 and level 2. Whether your level 1 is the original centered at a constant or the person mean version that subtracts out the level 2 is up to you. And this is chapter 8, by the way. It's one of the longer chapters in the book. And I typically go through an extended series of examples using both specifications and showing how, guess what, you can use estimate statements to go one way or the other. Between minus within is contextual. Within plus contextual is between. So you get 2, you can always get the missing third. However, and here's the picture that goes with this, the idea that we have taken the original predictor and retained it, added in the person mean. The original predictor, because it still has between variance, is partially predicting the between person random intercept, but we need this other one to get up to the full amount of prediction that is needed. So what could go wrong? Well, as I said before, this way is easier, but even the other way you could make the same complaint. Why are we making observed variables here on the x side when we're letting the model make latent variables on the y side? It's arbitrary. So let's not do that. Let's do this. Okay, ready? Camera 1, camera 2. Camera 1, camera 2. Okay, so do you know what this is? This is just multi-level modeling. This is for suckers. Do you know what this is? This is multi-level structural equation modeling. Doesn't that sound cooler? I repeat, multi-level SEM, hooray! Now, as you can tell from my presentation, here's the difference in how I talk about it. This is univariate, meaning we have one variable, y, whose variance is partitioned by the model, and we are doing the partitioning of the predictors ourselves using observed variables. What I refer to as this model is just a multivariate multi-level model, because we have a multi-level variance partitioning happening to more than one outcome. So even though we're conceptually thinking of X as a predictor, from the point of likelihood estimation, this is an outcome. We're letting the model separate out its variance components. We can then put relationships directly between the variance components. And these can be either undirected arrows, which are just covariances. You can do that in SAS, which is the example I want to show you. Or they can be directed arrows in which you have one random intercept predict the other. That, you need software that is capable of doing multivariate analyses, and this is where it gets its name. So this model that I've depicted here graphically, this can be estimated using single-level structural equation modeling. And Jonathan's going to show you this using Bayes on Friday. I'm going to show you this in M+ using just regular maximum likelihood. Or you can do it in the multi-level syntax of M+, in which case they call it multi-level structural equation modeling. Now, why do I make fun of that name? Do you see a measurement model here? Do you see items that make a factor or anything like that? No. The reason that people call this structural equation modeling is because random effects are latent variables. And by that same definition, if a random intercept can be a latent variable, so is the residual. Which is why when you have a structural equation modeling diagram, the observed variables have residuals pointing to them and the residuals are in circles. So it's not a coincidence that I have a shtick that goes with the book and my lectures with piles of variance. It's all coming together now. These are piles. These are random effects are latent variables, and so are residuals. So that's why they call it SEM. I don't call it that until I have an actual measurement model that has like between and within factors defined by items. Like that is where I would call it SEM. But if you are giving a job talk, any of you, you are doing multi-level SEM, damn it, because that sounds way cooler. So which way should you do it, right? And which way should you do it? I mean, univariate, multivariate. There's been a lot of relatively recent research on this topic. I can break it down for you. The pros of doing it multivariate. Well, it makes sense because why should Y get treated differently than X? There is some research suggesting that because you are assuming that the person means have perfect reliability when they don't, the level 2 between effects are downwardly biased when you use a person mean observed variable relative to a latent variable. It's the exact same reasoning by which people want you to do structural equation modeling rather than path modeling. You're supposed to be correcting for measurement error, and so the relationships among the disattenuated latent variables should be stronger as a result. However, where this starts to fall apart is in samples in which there's not a lot of information to estimate the level 2 random intercepts. So when you have a very low interclass correlation or a very small sample, the results that you get from the multivariate models tend to be a lot noisier than what you get from the univariate because there's just more stuff being estimated at the same time. It's harder to do. What are the cons? Well, if you're in multi-level SEM world, there's no such thing as REML. Think about it. You've never seen REML anywhere except in these models. It doesn't exist. So you're stuck with regular flavor maximum likelihood, and you're also stuck with no denominator degrees of freedom because of the limitations of software, not because of anything else. The other thing that comes into problem is interaction terms. So if I wanted to see whether the between person effect was moderated by some other variable, it's really easy for me to take my person mean observed variable and build in an interaction of it with something else. However, if my person mean has been replaced by a circle, now I'm talking about a latent variable interaction. Those require numeric integration. So how many you can have at the same time and whether they actually work is a lot more problematic. So these models get exponentially more complex because everything is latent. And when you have not a lot of data, that's not a good thing. So when you have variables in which there's only 2 kinds of variance, people differ in their mean and that's it. People have residual variation around those means. You can make an argument, reasonably so, as to whether you want to do boxes, univariate, or circles for everybody, multivariate. However, where you don't get the choice anymore is if the predictor itself has more than just between person mean variation. So let's say that you've measured something like, in older adults we have something like processing speed and memory, and we measure those each once a year for a decade. in older adults. And we want to know if changes in processing speed correlate with changes in memory, something like that. There's a lot of research that's phrased that way. Well, if we fit a model for memory, we might have a random intercept, some kind of random slope for changes in memory over time, and then we put in speed as a time-varying predictor. So we've got a person mean and a within-person deviation. That assumes that everybody changes in speed the same way. Probably not. And that doesn't even correspond to the way the hypothesis is worded. So then you're in a position where you'd have to try to make some kind of observed variable to go along with your two boxes that would capture change. And there's no good way to do it. That's how people used to do multi-level modeling before multi-level became a thing. It's called slopes as outcomes. And it's a bad idea. So you don't want to estimate separate regressions and take those slopes and go stick them over here. No, you need just a random slope for the x the same way you need a random slope for the y. So when you're in a situation in which between person variance can't neatly be summarized by just a mean, you got to go multivariate. Got to. This was in chapter 9. It's also in a paper that I'm currently working on because I still see this error all the time when I'm reviewing papers and I'm tired of writing about it. I want a paper where I can say, go read this. You can't do it that way. The other thing to think about then, in addition to just needing the slopes, is what is the intercept? So if everybody changes the same, it doesn't matter if you take the person mean or the first occasion because everybody stays the same in terms of their rank order. But if people change differently, your intercept or your mean isn't a good descriptor of how people are spread out from each other, right? It changes over time. So that's the other reason, is that you have to pay attention to that as well. So now we're in a situation where we need something like this. So this is a multivariate, multi-level model. This also goes by the name of multivariate growth model. If you want to feel extra fancy, it can be a multivariate latent growth model. Multi-level latent growth model structural equation model. The idea, though, is that we're treating the x and the y in parallel. We are letting the model find their random intercept variance, their random slope variance for change over time, and their level 1 residual variance. And then we can estimate either covariances or regressions among all of these different things at the same time. So if I have, say, a direct path, I'm asking, do people, let's say that the intercept is at the beginning, do people that start out higher on x start out higher on y? Do people who change more than other people over time on x change more than other people on y? And then lastly, at level 1, after controlling for all of that, if today I'm feeling worse than usual on x, do I also feel worse than usual on my y? Do these things sort of travel together within persons? So these are 3 distinct kinds of relationships that person mean centering could never fully adequately capture. So this is where we need some kind of multivariate model by which x and y can be treated the same. Okay, how are we doing? So do you want to learn how to trick SAS into doing the covariances version? What do you think? Yeah, maybe? You know? Okay, thank you. It's like, yes. So I put way more stuff in here than we're going to have time to go over. I will, let's see here. I'll show you what it's going to look like. So by treating both variables in the model at the same time, let me see where to start. Let's start here on slide 38. The other stuff in the middle is an argument for what else multivariate models can do. They're also used to test differences in effect size. So for instance, if I'm measuring improvement in depression as a result of an intervention, and I've got 2 distinct measures of depression, and my hypothesis is that my intervention is going to be more effective when measured one way versus the other, that kind of hypothesis requires both DVs to be in the model at the same time. So you would need these kinds of models to do that. So that's what the middle section is about. It's just other ways that these things can be useful in research. So slide 38. This is how we trick SAS or any other univariate multi-level modeling package into doing a multivariate model. We stack the data that was one row per occasion per person into a format that I call double stacked, because it's then going to be one row per outcome per occasion per person. So this is what it would look like if we had 6 occasions, 2 DVs. This is one person's data. So we have the outcome for DVA and for DVB. We have a categorical index as to which DV each row is for, A and B. We have 2 dummy codes that look like they're redundant, but they're going to be used as switches in the model. So DVA is 1 when we're talking about a data point for A, and likewise DVB is 1 when we're talking about B. And then we have our index of time. So let's say we have wave 1 through 6 here. Here's what a multivariate random linear growth model would look like, including the effect of one time invariant predictor. So note the colors here. We're adding another subscript. Colors keep track of which DV. So YTID, time individual DV, stands for dependent variable. So level 1 has DVA starting it off as a dummy code, which multiplies everything in the brackets. Likewise, we need a plus sign. It looks like the plus sign got left out here. Put a plus here, please. Plus, we have DVB multiplying everything in its brackets. So these dummy codes work like switches. When DVA is 1, we know we have an A outcome in the row. So that kicks on all this stuff. Individual intercept, individual time slope, time-specific residual. When DVA is 0, when we're talking about B, that kicks on the next line. So it's as if we have separate models for A and B, we're just estimating them both at the same time. Everything is being estimated separately. So then down here, I have an intercept and a slope for each variable, each of which gets its own fixed effect for the intercept and slope. It gets its own effect of a time invariant predictor. So this would be a main effect of the predictor. On the lines for beta 1, that would be a cross-level interaction of the predictor with time. And then each gets its own random effect as well. So this specification then allows you to directly test each fixed effect for each DV. So this is what it would look like in SAS. This way is more typing, but I think it makes it easier to understand what's happening. So we're using the double-stacked data set, where on the class line here I have 3 ID variables: person, wave, and which outcome it is. In the model, outcome is the outcome variable here. That is this single column that has all the outcomes in it. So we're lumping all the A and B outcomes together. Then we have our 2 dummy codes, DVA and DVB. And we have DVA times time, DVB times time, DVA times predictor, B times predictor, A times time, time predictor, B times time, time predictor. So there are no main effects of time. Time never shows up by itself, and there are no main effects of predictor either. All fixed effects are specified as clearly pertaining to A or to B. And the reason this is okay to have both of them in there is this option after the slash, no int. I shut off the global intercept. The one that's typically included by default, I don't want it here. So once that's gone, if you think about what A and B were in the data set, they're just a column of 1s and 0s, right? These are my new intercepts. DVA is the fixed intercept. It's going to hold the fixed intercept for the first outcome. DVB is going to hold the fixed intercept for the second outcome. And then everything else follows, just like the notation. On the random line, same idea. What do we typically write first after random? Intercept, right? That's not here. Instead, I've got my two intercepts, one for A and one for B. And I've got my two random slopes, one for A and one for B. Type equals UN. That allows all possible covariances between these things. So I directly get the model estimate of the covariances between the two intercepts, between the two slopes, int slope and slope int. The second set here does the exact same thing with less code. Because we put DV on the class statement, it understands that it has two levels. And rather than making it a contrast, because the intercept is gone, it goes ahead and uses both levels. So when I say DV, I'm going to get on my output a line for A and a line for B, because it understands that it's a class variable. Likewise, I can specify it with time and predictor. So this does the same thing, just less transparently. And then last but not least, the R matrix is going to be different than what we've seen before. Typically, subject has been person on these, but we have changed it to be person by wave. So these residuals are for the two DVs within an occasion. That's why we have DV on the line here. And type equals UN. That's different than what you've seen previously too. Typically it's type equals VC. We switch to UN so that each outcome gets its own residual variance, and we get a covariance between the residuals for the same occasion between DVs. Okay. Questions? Okay.
So where do we see the correlations between two residual circles?
That I did back a ways for reasons that escape me now, but on slide 29, this is what your G matrix is going to look like, where you have the intercept for A, the intercept for B, the random slope variance for A, and the random slope variance for B. And so these are the variances. The off diagonals give you the covariances, where I've highlighted in green the ones that would be of direct interest, int, and slope. If you ask for G core, you get the correlation version of this matrix, and you get all the correlations at level 2. Then the R matrix would look like, hang on, come back. Come on. There, that one. The R matrix used to be occasion by occasion. Because we've defined it as within an occasion, now it's just across the two DVs. And so we use it to be unstructured so that each DV gets a separate residual variance and we get their covariance between. And then we can ask for R core to convert this covariance into a correlation. There we go. This, by the way, is a picture of the idea of what that residual covariance would mean. If I had two variables that were both increasing on average, but they covaried together over time beyond that, that's this idea that they sort of travel together. People call coupled residuals, like there's a coupling, or correlated residuals. In the adult development literature, this is often a source of hypothesis as to whether things are really related beyond the fact that like you're both just getting older or something like that. So when would you do this? Well, The plus side is that you can do this in any software package that allows univariate models. So you can do it in any of the mixed things or LME or whatever. The downside is that all of your relationships between outcomes have to be specified as covariances. They only can show up in G and R for level 2 and level 1. So you can't test X predicting Y. You can't test X being moderated in predicting Y. You can't do mediation or things like that that involve direct regressions instead of covariances. If all you want to know, though, are differences in how the model works across predictors, and you're okay with the outcomes just being correlated, this is just fine. So for instance, if I had a hypothesis about whether my intervention caused depression to improve more in A's way of measuring it than B's, I can directly test whether the linear time slope for A is different than the linear time slope for B. Do you know how I would do that? Can you guess? Estimate, exactly. This time effect minus that one. And I could do the same for any contrast between DVs. If I want to know if an effect is bigger or smaller, then I can ask for any of that I want. So in, for instance, doubly repeated measures designs like you have, right? If you want to know if the change from pre to post is different in thing number 1 than thing 16, just got to ask for it. So this I consider to be multivariate multi-level. SAS is being tricked into thinking it's a 3-level model, but it's not, because time and DV are crossed. So I'm just estimating a time within person for A and B simultaneously.
So I got one concern when you trick SAS to do multivariate modeling, because it's doing it in like different conceptual ways. I just wonder how the SAS treats the degree of freedom at each level would be the desired way that you want.
It's going to use the same level 1 and level 2 as if the third level's not there.
So when we use different software, should we be like certain about like how they use the degree of freedom to?
The different options, yeah. So in SAS, we're picking an option for Satterth weight. There's another one that's Kenward-Roger, which is better for even smaller samples, but there's also between within that people use. Then you move over to something like M+, they don't have any of that.
So
There's no degree of freedom.
Oh, okay.
None. It's Z and chi-square. So that's the other advantage that this has, is that you can stay in REML, you can stay in the world of degrees of freedom for the denominator, and that works better for small samples. But it's limited in the kinds of multivariate relationships you can ask about. They all have to be phrased as covariances. And that doesn't work if you want to talk about prediction rather than just relation. So that's what I'll show you next time, is how to talk about prediction instead. And that moves us into the world of M+. Any other questions before we adjourn? All right, then office hours start now. Thanks for coming with me. Hope to see you all here for our very last class on Thursday. So sad.